Awesome. All right. Let's do some programming. So to see where we last left off, I'll just run the game. So last time we built this amazing piece of art. We got this bunny, all these funky blinking colors. And as you can see, there it's still really broken. We made the colors by using the vertex indices, just assigning a different color for each vertex index. Yeah, so there were a few things last time we ended. So one of the things we want to do was add a depth buffer. So as you can see with this model, it gives this really weird effect where things are in front are behind, things are behind are in front. Like it's right now it's just drawing in whatever order the triangles were submitted to the GPU. But we don't really want that. We want to render things that are in front of us, in front of things that are behind us. So another thing we want to do, once we have the depth buffer, is resize when we resize the window, because resizing window is nice. We also want, once we have the depth buffer, we can add some more information to our model. So we can add normal data. And the normals are basically directions of each vertex that tell it which way it's facing. It allows us to add really like smooth surfaces. Well, it makes a surface that's not smooth look smooth. Yeah, we need to do some transformation on those. Shading from scaling. We'll get into that. And then we want to do some basic shading with it, with those normals. And as bonus, like if once we've done that, I feel like streaming a bit more. We'll add some texture stuff to it. So let's get started with its depth buffer. So this depth buffer simply should be the same size as the screen buffer, but instead of getting an RGBA value per pixel, it's going to store a depth value, hence depth buffer. We're simply going to store that as a 32-bit floating point value. So let's add that. Let's call this our depth buffer. I think texture to D, depth buffer. And then we want a depth buffer view, depth stencil view. So the depth buffer DSV. And that's actually going to be all for creating our depth buffer. So let's see what is the best place would be to allocate this. I would say where we also build our swap chain. So let's just search for swap chain in our code. See what we do stuff with swap chain. So here we do some GUI stuff. We just find some stuff. Getting the swap chain size. Creating a random target view for the swap chain. Right, because swap chain, like the actual buffer of the swap chain we don't build. You create a swap chain, get the buffer from it, and then create a random target view for it. Resize swap chain. Let's actually look at our initialize function. Initialize graphics, awesome. So let's see what's going on over here. Create device, create a swap chain, create the random target view for the swap chain. So here we can start creating our depth buffer actually. So let's open new braces, create depth buffer. D3D11 texture 2D description. So like a depth buffer is just a 2D texture really. Let's set the width. which is going to be the window width, and the height, which is going to be the window height. Right, let's see, MIP levels. There is only going to be one MIP level. We're not going to do any MIP mapping, so one level. Array size, we don't want array, so the array size is 1. Format, well here it gets interesting. So we're going to do a D32 float. Or do we want to make it an R32 float? Let's just make it D32 float. The reason why I'm not sure what to make it is because sometimes you want to have a depth buffer that you can also read as texture, and then the D32 doesn't work. But this is our main depth buffer, and usually you don't read from that as a texture. Unless you're doing deferred rendering, I believe you do that. And actually we're going to make it a bit more interesting. We're going to use this strange format, D32 float S8x24uint. So this D32 float means a 32-bit floating point value for each pixel. The S8x24uint means we're going to have a signed or stencil, yeah, S for stencil. I was a bit confused, signed and then uint. So we're going to have an 8-bit stencil value for each pixel. And that stencil is something called the stencil buffer. And they're always combined together. This is just nice to have around. At some point, we might need the stencil buffer in some way. Let's just allocate it right now. If we don't need it in the end, and we really need the extra memory, we can just get rid of it. Right, disk. The sample description, I think, yeah, we have a count, which is 1. And quality is 0. These are just the default values for it. Usage, we're just going to do the default usage. Usage default. Cool. Desk.bind flags. Now here we tell it as well we can bind it. We're just going to be binding it as a depth stencil. If we also would like to bind it as a texture, we can also add bind shader resource, but we're not going to do that. With these bind flags, you really only want to pass the thing that you're actually going to be using, because if you pass stuff that you're not going to be using, the graphics driver can't do the most optimal path. And it may slow you down. Same for the CPU access flags. You set it to 0 if it doesn't need to be accessed by the CPU. MISC flags 0. Let's actually see if we need any MISC flags. D3. Let's go to texture description. Miscellaneous flags. Don't need that, don't need that, don't need that, don't need that, don't need that. Nope, don't need any of these. Let's not use any of them. Cool. So now, once we have that description, we can get our device and create a texture 2D, to which we'll pass the description. No initial data, and output a texture. And to our depth buffer pointer. Cool. And if we fail to allocate a depth buffer, which is never going to happen realistically, we'll just crash. We can add fancy error handling later on. Cool. So now we have the texture for the depth buffer. Now we need to give some parameters on how to actually bind this depth buffer and how to use it. And we do that using a depth stencil view. Let's create a depth stencil view. That's stencil description. That's D3D10. We're not doing D3D then. D3D10 is bold. All right, let's open this up. This is actually not what I'm looking for. Distance of view description. Ah, this is what I'm looking for. So here we pass the format again, and these formats can differ, but in our case, it's going to be the same. And like they can differ, but they have to match up in some way. So they, you can't have like an 8-bit, some 8-bit thing here, and a 32-bit value thing here. Like this could be R32 float and then D32 float. But we're just using simple depth stencil buffer. View dimension, which is going to be texture 2D, because we might have a 1D texture or a 3D texture. We're doing 2D texture. Flags. Let's look up both flags we can pass, just in case we need any of them. Oh, it always has this these really strange versions. I think it has like a bunch of C++ specific stuff that I don't like. Ah, that's better. I just want my plain old data. Read only depth, read only stencil. It's not going to be read only, I think. No, right, because we're going to be writing to the depth buffer. So I'll make it 0. Now, here for the next bit, as you can see here, we have a union. So when we set the view dimension parameter, we did that so that DirectX knows which of these structures it needs to read. We did texture 2D, so we need to fill in this one. And that's just going to be a MIP slice, which is 0, because we're only having one MIP level. Awesome. Let's create that the DSV, the depth stencil view. Depth stencil view. Awesome. Now we need to pass the resource first. Let's see what else needs passed. The description, and then finally the pointer to the a pointer to a pointer of the stencil view. So that one. Let's clean that up a bit so it fits on the screen. It's not liking that. Stencil view. I might have given this the wrong type. Yeah, I gave it a depth stencil state. This should be a view. Cool. And then let's also check for errors. And then crash if it fails. Awesome. Let's just run that code and see if it crashes or not. We're running. Looks like we're good. Alright. That's the depth buffer created. Let's actually use it. So here we have our test render function where we basically set all the state for the rendering system and simply call draw with our hard-coded value. And right here where we bind the render targets, we first have the parameter of how many render targets we bind, then an array of the render targets, and then we have this place where we pass a null value. This is actually where we place the depth stencil view. Right. Let's make that sure that fits within our boundaries. Let's run. Awesome. So it's running, but it's not working. Like we have this depth buffer, but we're not using it. It's bound, but we have set up the graphics pipeline to not use any depth. We did that last time just to get something running. Let's actually see where that is set. Where do we set it? Ah, right here. We set the depth stencil state to something that we called no depth stencil state. Let's add another one that's going to be less. So we'll only draw if the new depth is less than the last depth. Let's see, we'll create the other one. Cool. Create less than depth stencil state. We'll just copy this one. Less depth stencil state. It's a bit of a tongue twister. So this time we will enable depth. And the depth right mask is going to be all. This basically means we will write. And this will determine when we will draw the pixel. So you can set it to not write if you only want to draw something that is in front of something, but not actually update what is in front. So this is just going to be less. And we're not going to enable the stencil buffer yet. Only once we actually need that. Let's run. Cool. So create our depth stencil state. But it's still not working because we are still using the old one in the render function. So let's use the new one. And our image is gone. So why is that? So our depth stencil state is set to some value. We don't know what. And it needs to be less than. Let's say it's set to 1,000,000. And we draw our pixels and they're all less than. It draws all of them. For the next frame, they're all set to the values they were. So it's keeping the state between multiple frames. So if we move forward, we might actually see our model. We might not. Looks like it's initializing to 0, so we don't see it. So what we need to do with our depth buffer is we need to clear the depth buffer every single frame to be the most far away value, and then draw things on top of that. So we can do that really easily. We already are clearing our render target queue to black. We can just do this. Clear depth stencil view. Depth buffer, depth stencil view. Clear flags. Clear flag. Depth stencil depth. Cool. We're going to do 1 for the depth value and 0 for stencil value. So we need to pass some flags here to determine which of these buffers it needs to clear. Do we just want it to clear the depth, or do we also want it to clear the stencil buffer? So if we're not using the stencil buffer, we'll just clear the depth buffer. Awesome. Now if we zoom in, we can actually see it's rendering correctly. And if we go inside, we can see just the insides. So awesome, now it's working. We have a working depth buffer. Pretty nifty, huh? Alright, let's go to our checklist. Create and enable depth buffer. We did that. Awesome. Let's resize the depth buffer on the window resize. Cool. Yeah, let's find our resize function. I know I've created one before. At least I think I have. We might not have a resize function at all, actually. Yeah, we do have a resize swap chain. When is this called? Oh, it's right there. I just missed it. All right. So what we want to do here is we want to first delete the old depth buffer and create a new depth buffer. So deleting is easy. I just have this macro save release. I'll show you how it works. It just checks if the pointer is actually there. If so, call release, set it to null. Just make sure that so we can't call release too many times. And then there's this little do and while false around it so that it requires a semicolon. Just to keep the syntax consistent. You don't actually need that, but I like doing that. Let's see. Let's first get rid of the view, since the view depends on the buffer, and then get rid of the buffer. So now here we could copy paste that code for creating the depth buffer. Let's actually just create a function for it that we can reuse. Yeah, let's do that right here. Create depth buffer with a width and a height. And now let's take that code that we wrote earlier for the depth buffer. Let's see, where is it? Where is it? It's right here. Let's cut that and then call our function here. Window height, perfect. That will create our depth buffer. Let's go find a reset. Right, here it is. Paste that in there. You can now get rid of the scope. We don't need that scope block anymore. It's not doing anything. Hit create an H result. Rename this variable. Awesome. By the way, if anyone has any questions, feel free to ask. I love answering questions. Let's actually add a comment here. Create depth stencil view for the depth buffer. Awesome. So let's resize the window, see if it works. We crashed. Let's see why. So it's saying some stuff is null. Let's see, is our context still there? Let's see, D3D11, is everything still alright? The depth buffer and depth buffer stencil view is null. So I think we just forgot to call our function. Create depth buffer. Yeah, we cleaned up the old one, but didn't create the new one. We need to pass it within the height. With height, there we go. Right, let's see. Things seems to be working fine. Let's resize. Awesome, it's working. We can now resize our window again. Cool. Ooh, rabbits. Bunny, rabbits. Almost the same thing. Cool, so we can resize the window. So let's render the normal data as a color. So I was talking about these normals, and basically you gotta imagine that every surface that is flat, you can imagine a direction that's like right perpendicular to that surface. And that surface, that vector we can use to do lighting calculations. But if, for example, we're simulating something that's round, like this object, we would need like a lot of triangles to create that curve. So instead of doing that, we create few triangles, put normals of all the vertices, and then interpolate between them to make them appear smooth. And this really improves the quality of the final image. So let's use that to our advantage. So the normal is already in our buffer. We're just not reading it. So let's add that to the input layout. We create the input layout where we create our shaders. So we just add another line here. And we just say normal. Let's actually get our loading code from the asset system, because that's where we defined our vertex. Cool. So the normal is right next to the position. This is important to know. So we want the semantic name, semantic index. These refer to how we reference them in the shader. Then type, it's also 3 floating point values. Then we want the input slot. It's going to be from the same buffer, one bound in slot 0. And then it wants an aligned byte offset. So what this aligned byte offset means is really simply, from the start of the structure, how far do we need to go to get to this normal data? So for the position, it's 0, since it's right at the start. But for the normal, it's a bit further on. It's exactly a float 3 further on. And a float 3 is 3 floats. A float is 4 bytes. 3 times 4 is 12, so we need to enter 12. And the other parameters stay the same. So now let's open up our shader, test triangle, and let's add another parameter to our vertex input, the normal. Awesome. And let's also output that normal to our pixel shader. So in this case, I'm going to say output that normal is null. No, it's actually just going to be input that normal. We're just going to pass it on. The rasterizer will interpolate it for us. Cool. And let's actually copy this whole structure so it matches with the other shader. Awesome. Actually made a mistake here. I made this a float 4. This should be a float 3. There's only 3 values in a normal. It's just an X, Y, and Z value. Awesome. So now we can actually draw that normal. And because the normal is in a range between -1 and 1, we'll multiply it by 0.5 and add 0.5 to it. There's actually another thing we need to do. Because the rasterizer interpolates, the normal we get out of this might actually not be a normalized normal. It might have a length of 1. So what we'll say is float 3 normal, normalize, input to normal. Luckily, HLSL just gives us a function for normalization. And we'll draw that. And that should be it. Let's try it. Doesn't like normalize. Why does it not like normalize? So it's actually saying some stuff here. Let's read this. Float m. No matching one parameter intrinsic function. Huh. Oh, input normalize should be input normal. Haha. It was thinking that was a function call. Or doing something weird to it. Ah, there we go. So how do we read this? Like, we have all these fancy colors now, but what are we actually looking at? So remember, we have the three world axes. We have an x, y, and z axis. The x-axis is mapped to red, the y-axis is mapped to green, and the z-axis is mapped to blue. So as you can see, like this is pointing towards x, on the top everything is pointing towards y, so at the bottom we should be seeing no green, which we aren't. So this is the normal data that's pointing out the surface that we now visualized. And as you can see, if we zoom in on the model, we don't see like the triangles anymore. They're all interpolated nicely. But this normal data is actually pretty useless to us right now, because it's all in the local space of the model. It's viewing it as if the axes are attached to the model instead of the world axes. So we need to convert this to world space. And we can do that using our world matrix. So where we added the worldview projection matrix, we'll just add another matrix, the world matrix. And we need to create one of those in our D3D11 code. Let's see. Right. So in the test C buffer, we'll add a world matrix. So this matches with the constant buffer in a shader again. Let's just say where we created the matrix. Yeah, that's where it is. Awesome. And since we already created our world matrix, we can just say world matrix. Cool, let's run that. We passed our shader, but we're not doing anything with it, so let's change that. So we want to multiply the world matrix with a normal. Now the normal is a 3D floating point value, like it's 3 floating point values with a 4x4 matrix. We can't multiply that unless we make this a float 4, or we cast this down to a 3x3 matrix. So let's just do that. Cool. As you can see now, the right is always red, the top is always green, and the back is always blue. So now these normals are actually stuck to our axis system, our world space system. Let's go look at what we were trying to do again. So we rendered the normal data as a color. That was actually pretty easy. And we transformed the normals into world space with the world matrix. Now there actually is another problem here. Oh, let's actually not say that. There's another problem here that we haven't solved. And I drew a little thing for that to explain. So let's say we have this triangle and we have this normal facing away. If we scale this uniformly, everything is going to work. But if we were to scale this in the y direction, I would also scale our normal in our y direction, it's not going to be perpendicular to the surface anymore. So what we need to do is figure out a way that we can actually change the normal to be correct again. And it might be a bit difficult to see, but with this first triangle, the angle it's going at, it actually needs to go the reverse direction than just when you scale it. Oh, hold on, my screen's turning into night mode. That's actually really annoying. Let's turn that off. Awesome, we have good colors again. So we need a way to convert to this this system, and we do that with something called a inverse transposed world matrix, which most people just call the normal matrix. So instead of calling this world matrix, let's call this normal matrix. This matrix is just going to be here for transforming normals. Let's also rename it in our C++ code. And what we can simply do is inverse the matrix, for which I've already made a function that I really nicely copied from an open source library that I put a reference there in it. And let's then transpose it. And transposing, what it basically does is swap columns and rows. And once we do that, we should be getting the same result, but it will work once we start transforming non-uniformly. And this is just there, so we don't end up with a bug. We don't end up with a bug where all the lighting is wrong and we don't really notice and it's in there for like ages. We want to fix this like right away. Awesome. We're actually going through this really quickly. So now we can actually do some shading with this. So we want to do the shading for each pixel. Let me have a little sip of tea, I think, for a second. Right. So to do shading, we're going to be using the normal and something called the light vector. Let's open a new thing. Cool. So let's say this is our surface. And can I do shapes? Can I do this? It's just selecting. I really don't know this program too well. Shapes. Can I select a shape? Yes. I want an eclipse. That works. So let's say this is our light. This light, let's just actually also draw that normal. Nice arrow. Really beautiful arrow. And this light is shining onto the surface like that. Now the shading is going to change based on from which angle this light is coming. And to calculate that exact shading, it depends on the surface that you're trying to simulate. So if you would have something that's like really reflective, you would use something different than something that's like really diffuse. We're just going to do the most basic thing for our shading right now, and we're going to do something called Lambert diffuse. So the Lambert diffuse basically takes the position from like the position in the world and then creates a line to the light and then normalizes that line, the direction. And then it simply takes this angle, takes this takes the angle between two vectors and does the cosine on it. So when this angle's, when it's shining right at the surface, the angle is 0 and the result's going to be 1, so full lighting. If the light would be like right over here next to it and it's shining like right, oh, where did my line tool go? My lines are broken. Why did my lines break? Okay, let's just do this. So if it's going like right next to the surface, it's going to be a really big angle. It's going to be a 90-degree angle. A 90-degree angle in a cosine is 0, so there's going to be no shading. If the light is behind it, it's going to be some negative value, so we'll clamp it. So the least we can do is 0. We can't have like negative lighting. That would be really weird. So calculating the angle between two vectors and then do the cosine of it sounds like it's a really expensive operation. what we can actually do is just simply do the dot product, which will give us the exact same result. Like it's defined that it is that. But the dot product is really cheap to calculate. It's just multiply the x values, the y with the y, z with z, and then add them all together. So we'll go for that. Now there are also different types of lights. So right here what we have, it's actually a bit of an area light, but let's call it a point light for now. It's like a single point that's shining in all directions. What we can also do is create a forgot I can't draw lines, which is really annoying. What we can also do is draw is use a directional light. The directional light basically simulates the sun. So imagine a light that is infinitely far away. And if it's infinitely far away, all the light rays are going to be parallel to each other. So we can just create a single light direction for every point on the model and use that. And that will allow us to just simply hard code some light vector and then use that. So let's code that. So we need some light vector, which we'll fill in later. It's going to be something. And we're going to do shading is the dot product of the normal with the light vector. We're going to say shading is saturate shading. And what saturate does, it will clamp it between value that's between 0 and 1. Let's actually just put it around the dot. Saturate. And then for the color, we can do white. Let's say for the color, it's white. 1 is white. And then we can just output simply color times shading. So for this light vector, let's just do a really simple float 3 that is 0, -1, 0. No, actually a 1. So this light vector is pointing up, which means the light is coming from up. Because the light vector is from our surface to the light. Let's see what this looks like. We are not seeing anything. Let's see, we created a bug. What happens if we set the shading to 1? Okay, we get white. Let's say we don't saturate this. We just do the dot product. We get black. Normal, light vector. That's really strange. I mean, this looks fine to me. And let's just add some value to shading so we can actually see anything. Okay, it's really, really dark. Let's add a half. So are we getting any different colors? Ooh, I'm noticing my camera is still not working correctly. Rotation wise. This is not moving up and down. So this dot product is, I'm putting 0. So we drew the normals, and the normals looked fine. See, normals are fine. And if we draw the light vector, we should just be getting green. Ah, I made the light vector single floating point value. Yeah, that's the thing I hate about HLSL. Is that it implicitly costs a bunch of things. Alright, there we go. We see something and it looks a bit shaded. Let's improve this a bit. Let's get rid of that ambient color. Let's saturate this again. Awesome. So we have this light shining from above on our little bunny, and it's looking nicely shaded. Now let's make sure this is always normalized and play around with this vector a bit. So let's say it's also coming from an angle at the side. That looks great. And now also, like from behind us would be awesome. Well, that's in front of us. Let's move it behind us. Awesome. So now we got this nice shading angle. And what we can do, instead of calling this shading, let's call this Lambert diffuse. As the shading is Lambert diffuse. So we can also add extra lighting to this. So we can also add an ambient term. Ambient. I will just set this to some value. So in real life, light doesn't just hit a surface and then goes to your eye. Light bounces all around. Like a red surface next to a white surface will make the white surface look a little bit red. This is something that's often called global illumination, and it's like a big thing in games these days. We're not going to be simulating global illumination right now. So we sort of fake it by adding an ambient term. So we have some light if the light is not shining directly on it, so we can actually see it still. So this is from behind, we can still see the bunny. Alright. And you can see it's also a bit brighter now on the light spots since we just added value. So the ambience, it sort of works to show us something, but it's really a really fake effect. It will do for now though. So we did basic shading with the normal. We actually went through this really quickly. It's been only 15 minutes. So we can do some bonus stuff. So we did the normals. Let's also add the texture coordinates. So texture coordinates. Let's talk about texture coordinates. Let me grab my drawing thing and see if I can draw a line. I can draw lines again. Okay. This file is just broken or something. I don't know. Let's say I have a texture. Texture. And imagine this is a square. And I am, it's like a beautiful texture that's like cool texture data on it. Look, art. And now we have a triangle. And we're trying to draw this triangle. And we're trying to basically put this texture on this triangle. But let's say we don't want the whole texture on it, we just like want some part of the texture on it. So let's say that we want like this part of the texture on our triangle. So this can really simply be done by for each vertex of this triangle, we simply store the position in the texture for it. And then with the rasterizer interpolating all the values in between for us, it will get all these values in between on our texture. And we can use those coordinates to sample from the texture. Now these coordinates are not in pixels, but they are in a normalized space where you basically have this axis. Oh, let's make that a line. You have this axis. Oh, my lines are broken again. It's because, oh, it's because I have something selected. Okay. So this is our u-axis, which basically is the x-axis. And we call this the v-axis, or simply y-axis. Depending on the graphics API that you're using, v is either pointing up or it's pointing down. I can't quite remember which one it is in DirectX. I know it's different for OpenGL, but what I usually do is just see if it works, and if it doesn't work, we flip it. And I usually flip it during model loading. So I'm not sure if that bunny has any good texture coordinates, but I don't really care. I just wanted to see some UV coordinates or texture coordinates. I see some texture mapped on it, no matter how ugly it is. Because if it works, it will work for all models. So let's implement that. That's the wrong Visual Studio. That's the right Visual Studio. Awesome. So again, just like our normal data, we already have our texture coordinate data actually loaded up. We're just not using it. Let's add it to the input layout. By the way, if any of this is confusing, feel free to ask questions if you want to have this explained more. So for the texture coordinates, it's only going to be 2 floating point values instead of 3, because it's a 2D texture. So we'll put this format at R32, G32, 2 floating point values, and we need different offset. So the offset from here to here, from here to here is 12. So one float 3 further is simply another step of 12, which is 24. So we'll say 24, and then DirectX knows where to read our texture coordinate data. Then we can add this to our shader, our vertex shader. Export. And this name matches with the one in our DirectX code. And for output.text chords, oh, actually, let's add it here first. So we want to output a texture coordinate as well. Export. Output it to the rasterizer and into our pixel shader. So we don't actually transform anything on the texture coordinates. We just pass them. And then in our pixel shader, we should need to update our structure. Let's do that. Awesome. Let's get rid of our shading stuff here. And let's add this. Instead of drawing our shading stuff, let's draw the texture coordinates. So we need to return a float 4, and we can fill the first 2 slots with our texture coordinates. We'll just put that's blue at 0 and 1 for the alpha. And let's run that. And that breaks. Incorrect number of things. Right, I actually accidentally made this a float 3 instead of a float 2. So let's go fix that here as well. Now it's a float 2. And that crashed. Let's see why it crashed. Failed to find useful renderer. Oh, right, because that's the error message it gives when it crashes. So our shaders compile. This seems fine. Text chord. Let's actually let's put breakpoint there. See if it breaks right there. -6 for the result. All right, let's actually step into that function. Read file. filter read the file. Okay. Hard. Read the actual file. Close the handle. Bytes red matches size. Turn 0. Now it seems to read the file. It's strange. Input element count. Oh right, this is a different file we're stepping through. Let's actually step through the red one. Oh, I missed it. Let's restart the program. There we go. Get file size 1. Yeah, that's succeeded. High part is 0. Low part is some value. Buffer max size. Oh, it's passed some random max size that I set up. Right, because I only have a 16K buffer. Let's actually make this a lot bigger. That's because I didn't want to do any memory allocations, so I passed the past the buffer, but our shader actually went past the size and then failed to load. Alright, let's see if it works now. There we go. And as you can see, these are our texture coordinates, and for the most part, it's really smooth. But there's like this one part where it transitions, so we'll get like a hard edge there, which is fine for a testing model. And then there's one triangle that wants to be different, or two triangles. No, just one. Well, we'll let him be different. We're not going to be mean to him. So these are our coordinates of the texture, but then mapped to a color space. Cool. So let's load some texture. Yeah, we can add this to our asset system for test loads, where we wrote our testing code for loading some testing model. Let's actually do test load texture. And let's create our texture ourselves. So this texture is going to be 1024 by 1024 pixels. The reason why we make it that weird size is the GPU really likes powers of 2 and really likes textures that are square. So what you'll find, most 3D games will only use textures that are square and a power of 2. And one of the advantages of power of 2 is that it makes mip mapping a lot easier, which we'll get into at some later point. We're not going to do that right now. So let's draw a really cool texture. Let's make it blue, and let's have green lines, and let's let it. Oh, it's really thin. I want a thicker line. I mean, I'm a real artist here, so it's gotta be beautiful. 16 pixels wide. H L L O. Hello. And a smiley face. Let's actually add some cool like fire effects. Like there's fire here, and at the bottom, how do we get a dark green in this? More. I can actually add a bit darker. We're gonna have grass. This is some real art skills right here. Drawing with my mouse. Cool. We've got ourselves a really cool texture. Awesome. Cool. Let's save that. save as a PNG. Let's actually move to our data. That's Bitbucket. Assets. Awesome. Test.png. Let's store it as 32 bits. 32 bits per pixel. Awesome. Beautiful. Yeah, so this model loading library that we have actually comes with a really cool library for loading images, which I really like. It's called STB, and it allows us to just call STB loads with a file name, PNG, and then we just give the width, height, and component counts, in which you can output, and then we say we want at least 4 components. And that returns a by UC, so it's unsigned character. Let's just start buffer with our pixels. Yeah, that is the loaded texture. Who would have known? Since I know what the format of the texture is, and this library doesn't, I know it's going to be 4 components. It's going to be 1 byte for red, 1 byte for green, 1 byte for blue, 1 byte for alpha. I'm just going to output this as a 32-bit thing. That's a 32, out width, out height. Let's put these below each other. Awesome. Out width is going to be W cast to width, height, and then a buffer. It would be really nice if I could like type things the first time, but not going to be going to be the case today. Cool. So let's call this function in our game code. Game. Right here we loaded the texture. Let's say load test texture. Let's go to this. Texture buffer. Just call this texture width, texture height. Cool. Let's add these to the game. Game memory. That is going to be pointer. Let's add some semicolons. Some happy little semicolons. Cool. Semicolon here. Cool. That's all added there. Now we need to add it into our graphic system. So we'll just create another text function, upload test texture, buffer, width, height, awesome, upload test texture, cool. Then we can create an implementation for that, or actually just call it right away. Upload test texture. Texture height, awesome. Let's put these all in lines. Cool, and let's assume nothing goes wrong. In our test load texture, let's actually say if buffer is null. So if we fail to load the file, we'll just crash. Since it's testing code anyway, we didn't really care. So let's add a function for that. Upload this model will just be upload this texture. We'll just put this function right after that other one. Ooh, I just deleted everything accidentally. I wanted to paste something. And it's going to be the buffer, the width, the height. Awesome. So let's take everything that we need and stick it in our DirectX 11 data. Just create our data right now. So let's see, where did it create vertex buffer and index buffer the total here? So let's add the texture right below here. It's going to be a texture 2D, just like our depth buffer, which is going to be our text texture. This should be a pointer. And this time we're going to have a shader resource view. And what the shader resource view basically means is something that we can bind to a shader. And then there's one more thing that we need. A sampler state. A sampler state describes how the GPU should sample from a texture. We're just going to be using the most simple sampler state. We're going to do doing something called point filtering or nearest neighbor filtering, which is going to be the cheapest and the ugliest, but it will allow us to just show the texture. Point filter sampler state. So let's create our test texture. Sheet that text 2D description. Description dots. Let's look at all these parameters. Width is width. Height is height. So far so good. Map levels. We're just going to be doing 1. We will have more for our textures in the future, but right now let's do 1. Ray size is 1. Format is going to be DXGI format R8, G8, B8, A8, unorm. Now what is unorm? This unorm is basically reads integers and converts it for us to floating point values. So if we, for example, take our texture and would be just looking at the red channel, there's basically going to be values that are between 0 and 255 for how red every pixel is. Same for how green every pixel is, same for how blue every pixel is. Just like the RGB values on the color picker. Calculating with values between 0 and 255 is actually really annoying, and we'd much rather calculate with values between 0 and 1. Now, to do this manually would be really annoying. So luckily, the GPU actually has hardware built in to that for us and also do it really, really fast. And then there's actually another variant of this, which is sRGB, which is something we'll also be getting into later. I'm just going to not do that right now. So we need to set a count, quality, quality 0, usage always default. This is only really useful if you're really trying to optimize stuff, or if you need to stream data into some GPU resource. Bind flags. This time we're not going to do a depth buffer bind flag. We're going to be doing a shader resource view. Bind shader resource. CPU axis flag 0. We don't want the CPU to access this. Miscellaneous flag 0. So let's add an H result here, so we can check for errors. Create a 2D texture. Pass the description. We need to set up our initial data because we're only going to be uploading to this once. So let's do that. Sub-resource data. So the memory is going to be the buffer. Width is no, that's not width. It's pitch is the width. That's actually not the pitch. Pitch is the width times the size of UN32, which is 4 bytes. This is the pitch in bytes, not in pixels. And here we do width times height times size of UN32. So a slice is basically only needed if you're doing 3D textures or like a cube map, where you need to tell how big like a 2D thing is in the 3D thing. So if you have a cube, basically, how many bytes does it need to move forward to move up in Z value? So let's pass the pointer to that thing. Now let's output to our test texture. And if we fail, we'll simply crash. Awesome. Now we need to create a shader resource view, which will describe how we will read from the texture in our shader. Let's open the thing for that. So we'll give it a format, which is going to be the same. View dimension, which is going to be 2D texture. And now we have to do this. Like I explained the union before. We have to fill in the texture 2D1. Most detailed MIP, 0, which is almost always going to be 0. Since MIP level 0 is the most detailed one. MIP levels, only one MIP. We're not doing MIP mapping yet. Let's take it one step at a time. Yeah, give the description to that. Oh, hold on, that's the wrong function. Yeah, I need to pass the resource first. I was really confused there for a second. That's texture. Pass the shader resource view description, and then a pointer to a pointer for shader resource view. Texture as awesome. Cool, and if we fail, we'll just crash. Let's try running that. Awesome. So we didn't crash, which means so far so good. Everything is fine. Let's create that sampler state so we can start adding our texture. And the sampler state we'll just create where we'll create at the place where we create all the other states that we bind. So create point filter sampler state. Sampler disk. Let's see what we can fill in for this thing. I actually can't quite remember. So we need some filter. Let's see what filters does. Okay, so we want to do min, max, midpoint. Okay, so basically there are three different things it needs to filter on. So if it needs to minify the texture, so it needs to make it smaller. If it's smaller on screen than it is, than the texture actually is, what does it need to do for minification? We also said what it needs to do for magnification, so what if we make it bigger? And then what we need to do for mid mapping we're not doing yet. And the way the syntax works is if it's the same as the next thing, you skip it. So minification going to be the same as magnification is going to be the same as mip, and mip is going to be point filtering, nearest neighbor. Let's add an addressing mode. So we talked about the UV coordinates and how they're between 0 and 1. They can actually go beyond 0 and 1, and they could be like 10. So we tell it what to do when it goes out of bounds. And we're just going to do wrapping. So if instead of 1, we get 1.5, we wrap it back to 0.5. And that way we get sort of a repeating effect. And most models are built, they are made to use this effect. This is also like how you would repeat a texture on a big plane. You can just simply use the wrapping option. You could also add more vertices and then do all the UV mapping on that, so it's between 0 and 1. You could do that, but this works fine as well. So we need some LOD bias. We set it to 0. It's for mid mapping. We're not doing that yet. Max anisotropy. We're not doing anisotropic filtering, so we'll set to 0. Comparison func. Now this I think we also don't need. This is if we're doing a special sampler for comparing depth values. So I think we set that to 0, or we just don't set it. Let's actually look that up. I'm not sure. Let's see. Never pass comparison, always pass comparison. The comparison option is declared in the description before an object is created. The API allows you to set a comparison option for a depth stencil buffer. I think if we just don't set it, it's going to be fine. So what we'll do, comparison func is question mark. I will just comment this line. So we're not sure what to do with this. The border color. So remember when we did the set that we want to wrap the texture, you can also clamp the texture, and you can clamp with a border. And clamp with border basically means is anything gets outside of the range, give it the border value. And here we can set the border value. We'll just set them all to black. We're not using them. Min LOD 0, max LD, I think this needs to be like float max or something. Might not even matter for our simple point filter. Yeah, to have no limit, just set to D3D11 float 32 max. Let's just do that. Let's see what the documentation tells us to do. And then we can finally create this thing. Create some persistence. Come on, Tessence. Awesome. Desk. That's actually point filter sample state. And if it fills, it'll simply crash. Let's take the address of that. Cool. Awesome. We have sampler states. Let's actually go use all these things that we just created to do something useful. So in our rendering function, we want to bind some extra state, and we bind this to the pixel shader. We also need to add our pixel shader a bit. So let's open up our pixel shader next to the other shader. So we're going to be adding, I think you just do this. Yeah, which is our, let's call it the albedo, which is I think like the official name for the color. And we need to bind this to register, which is going to be T0, I believe. And let's get the sampler state. I can't use sampler, sampler's reserved, so let's do sampler underscore. I think it's S0 for sampler states. And now in here we can say PS set shader resources. And this one's our start slot, a number of views, and then array the shader resources. We start at slot 0, which is this slot. Only do one of them, and to sort of simulate that we have an array of them, we just take the address of our one shader resource view. Test texture as ooh, sure, so there we go. And then we also bind the sampler. Set samplers. So also 0, 1, just the one. Point filter sampler states. Cool. So let's actually use these. So to sample something, just the sampler, let's sample from our albedo texture and the pass texture coordinates. And that will give us a float 4, and that will be our albedo. Let's actually call this the albedo map. And call this just the albedo value. And let's output that. Let's see what it looks like. It looks like error. We did something wrong. Sampler state object does not have methods. Oh, then I might have these wrong. That's probably texture.sample and you pass the sampler. Incorrect number of numeric type. This should be, yeah. So we'll only take the XYZ values. We'll actually do that right here. Just take the XYZ value. Because we don't have any alpha in our texture, so we'll just ignore that. Awesome, and we can see our awesome texture is mapped in a really weird way to our model. But you can definitely see it. Like here's hello, and here's the fire that we created, and here's the grass actually. The grass is on his ear. He has grassy ears now. What we can do now is take our old code and combine it with our new code and actually shade this texture. So color, we'll get rid of color and we'll call that albedo. And with all the shading times the albedo color. Awesome. Now you can see the shading is back. We got our nice lighting, and we got our textured beautiful body. So let's look at our goals. So we loaded the test texture and we drew the test texture on the model. Awesome. How long have we been going for? Almost 1.5 hours. So what I'm going to do, I am going to take a short break, and then do maybe like 1 or 2 things that we can still do, and then end it there for now. So Yeah, let me have a short break. I'll be back in like 5 minutes, and we'll do some more coding. All right, see you in a sec. Alright, I'm back. Um, so I was thinking for a bit what I can do in like not too long. Um, One thing that came to mind is really easily, she made a list, added to the list, is backface culling, um, which I'll explain when we get to it. And the other one is I want to make a flat plane in code. Um, and that flat plane is going to be used for something because of what I really would like to build at some point. Well, actually, what I would just like to build is sort of a water simulation. That would be really cool. Other things I want to build, I'll just make a little to-do list. I want to add a skybox so that like the back of our like except for like a 3D model, everything is black, which is not that great. The skybox is really nice. What I also like is stuff like maybe some world based on a height map, where you basically just have a 2D texture with a single channel, and then every pixel just tells you how high a vertex is. So for the skybox, I need some asset file that is free to use. And that's sort of the difficulty with finding art is if it doesn't explicitly say you can use this for free, you should always assume that you can't. So generating this flat plane in code, it's going to be useful for a water, but also for that height map. Since our height map is basically just a flat plane where you adjust the vertices based on the data in the height map. Yeah, let's do backface culling first. So let me explain what that is. So when we fixed the depth, we added the depth buffer on our model. It was because triangles that were behind the triangles in front were showing up in front, so it was all reversed. So we could see some sort of sometimes you could see the inside of the rabbit, of the bunny, rabbit bunny. I still don't know the difference. But what I actually notice now is that we don't see the inside at all, but we are still rendering the inside, and that is wasteful. Like if we go inside this bunny, we can see the insides of the bunny, and we can still see shading, which is also wrong. We shouldn't be seeing any shading since it's black in there, but that's shadows. We don't have shadows yet. So what we can actually tell the GPU is we can let it do a test that if the triangle is facing away from the camera, to not draw it, to cull it, hence backface culling. So when we go inside, we'll just see nothing, which is fine because in a game you never want to put the player inside a model. you wanted to see the world, not like the inside of a rock or whatever. So adding this is actually not difficult, but it's always a little bit of tweaking depending on how the data is laid out. So let me explain how this backface culling works. So let's draw our trusty triangle. Oh, that's green. I want black for this. Awesome. Let's make it a little bit less white. That's perfect. So we have a triangle. Ooh, triangle. Let's actually add a second triangle. Cool, true triangles. So when we assign the indices, we can do this in two directions. We can do this. Oh, that's really tiny. we can call this 1. We can call this 0, call this 1, and call this 2. But what we could also do is call this 0, call this 1, and call this 2. So basically you can go clockwise or counterclockwise. It doesn't really matter which direction you go, as long as you're consistent. And the nice thing about this property is that if we rotate the triangle, it will be mirrored, and the rotation that we're going on will be flipped. So you can imagine. Wait, maybe you don't even have to imagine. What if I cut, paste? Yeah, if you rotate the triangle, haha. Rotate the triangle. Actually, that's rotating around the x. The z-axis need to rotate around x. If we, how do I flip things in here? Oh, I got a notification. OBS. Reconnection. Oh, it looks like it disconnected for a second, but it reconnected. Is the stream still fine? Yeah, stream seems to be fine. All right. It's actually rotating around that axis is fine, but if we were to flip it, I'm not sure if I can show it, but you can imagine it. If we were looking at this from the back, it would be flipped and the order would be in the wrong direction. And we can use that fact to determine if triangles are facing towards us or away from us. And if they're facing away from us, we simply just don't draw them because we're not going to see them anyway. It's a waste. So this is done in the rasterizer state. So instead, we already have like our default rasterizer state. So let's also add a callback rasterizer state. Let's find where we create our default one. Awesome. We can create callback rasterizer state. And we can simply copy these. Awesome. So we're going to keep everything the same, except for the curl modes, we're going to say callback. You can either say curl none, curl front, or curl back. I think there are some graphics APIs where you can also say curl all, which is a bit weird because you might as well not draw anything. But DirectX 11 doesn't give that option. So we're going to be doing the culling from the back, and then there's also this parameter, which will say, is the front counterclockwise or clockwise? And we can tweak this value depending on how our model data is laid out. I don't know how our model data is laid out. I think it's counterclockwise, so we'll just see if we get something that looks right, and if it doesn't, we'll just make that false. Callback rasterizer state. So instead of binding our default rasterizer state, we'll just call the callback rasterizer state. That should be it. Right. So as you can see, our model looks different, and it looks really weird. So now we're only drawing the triangles that are facing away. So our triangles are clearly laid out in a clockwise fashion. So we'll just say front counterclockwise is false. It's all clockwise, and let's also change that here so we're consistent. Even though it doesn't really matter for this one. There we go. So now if we go inside the model, you'll see it's gone. There's only the outside of the model, the part that we actually care about. And this is just a little optimization that we can do. That's just good to have turned on from the start. We don't want to rely on any backface culling stuff. So that's the first thing done. That's backface culling done. Let's generate this this flat plane. And I'm thinking about where we would generate this. I'm not sure where the best place would be. Um, so I might as well just generate it in the graphic system. We can always move it somewhere else later. Let's just do it in the graphic system. Yeah, just to keep it simple. So let's add a new function, internal void D3D11 generate plane mesh. Cool. And we'll give it a like a number of vertices along the x-axis. Vert count y. And what we'll do for this plane, if let's say this is our plane from top down. Let's actually make these lines. And we'll have like more x values in here. Well, I say x values, with these I mean vertices. Cool. So we have these vertices. So this would be like a 3x3 plane. We will always make sure that this is going to be 0 to 1 and that this is going to be 0 to 1. Because this will allow us to later, with a matrix, scale it up to any size that we like. This vertex count x, let's just say vertex count x and vertex count y, is just there to determine how many vertices we want on there. Basically, how precise we can make that plane mesh. And this will be useful later for applying our height map, since we'll just be able to pass the width and the height of the height map, generate a plane, and then adjust all the y values, recalculate the normals, all the jazz. But we'll do a flat plane first. So let's determine the number of vertices. The total number of vertices is simply going to be the vertex count x times the vertex count y. We'll need to allocate a buffer of vertices. Let's call our own malloc function, which is the vertex count times size of a vertex. And for ease of use, let's just memset that thing. Let's 0 the memory. But just clear to black, easier to debug. Now we need to go to the y-axis. And we want to have a float y at 0 and a float x around x. I will create some deltas. So delta y is going to be 1 divided by vertex count y. And I might need to -1 here. to make it end up at 1 at the end. Let's see, if we have two vertices, we want 0 to be at 0, move it by delta y of 1, 2 minus 1 is 1, 1 divided by 1, yep, we want this. Dx dy. And here for every scan line, we'll just say fy plus equal delta y, and here we'll say fx plus equal delta x. Let's also add a counter. And we can say vertices, just create a vertex v. I will just say vertices I is v. V dot position is going to be make f3. So for x, we just do x. Now we say y here, but what we actually mean is z. So the y is going to be 0, but we're going to insert our y into z, because z is flat, is from us towards us, and x is from left to right, which I think is like reversed because of my camera, so left to right, yeah, like that. Then we can also add a texture coordinate. Let's make the texture coordinate the same as our position, so we also have a 0 to 1 mapping. And let's make the normal just point up, which makes sense for our flat surface. So we generate vertex, and here we store vertex. Awesome. This will create the vertices. Now let's do the indices. Because we've got all the points, now we need to create triangles using those points. Let's see, how many how many indices will that create? So if we have 1 point, we have 0 triangles, 1 by 1. 2 by 1, we still have 0 triangles. 2 by 2, we get 2 triangles, so 6 indices. 3 by 2, let's actually write this all down. 1x1, 0 triangles. 1x2, 2x1, 0 triangles. 2x2, 2 triangles. 3x2, 4 triangles. I'm just trying to, like, writing some stuff down and see if I can find the pattern. So that's 6 triangles. I would say if we have 3x3, so that's 8 triangles. That's going to be, 4x4 would be, let's see, let's just draw this. I love drawing things. Drawing things really helps me figure out what's going on, so I can just see it instead of trying to imagine it in my head. Let's see. Awesome. So we have 18 triangles. So what my theory is, it's width minus 1 times height minus 1 times 2 is the number of triangles. And that times 3 is the number of indices. So to make this function a bit simpler to use, let's just assert that we always have more than 1 in both resolutions, because it just doesn't make sense to make a plane that's 1 vertex. Yeah, let's do that. So the index count is going to be vertex count x minus 1 times the vertex count y minus 1 times 6, because 2 times 3 is 6. And then we'll say, we'll allocate an index buffer. And we'll also zero that memory. Right. Now we need to generate these indices, and we need to do so in a clockwise manner. How would we do that? So what we can do is simply just loop through the vertices and then skip the last one and just say x and x plus 1 and y plus 1 and then x plus 1 and y plus 1, which will give our four vertices each time. And then for that we generate indices in our index buffer. Yeah, that sounds good. So let's do that. Cool. So let's calculate these values with offsets. Now we don't need to actually load the vertex data. But we need the index of the vertices. So, right, so we have ID of 0, which is going to be x0 plus y0 times vertex count x, the way our data is laid out. Yeah, and we'll offset this like this. So we'll have 0, 1, 2, 3. So to push the indices, let's actually have a counter here. We'll increase this with 6. Do 0, IDX0, IDX1, IDX2. So that's this 0, 1, 2 clockwise. Then we want to do the other one clockwise, which is going to be 2, 1, 3. It's 3, 5. 2, 1, 3. So check out 2, 1, 3. Awesome. And that should build our entire index buffer. And that's generating a plane. So this is actually not DirectX specific at all. Let's not prefix it with this. Let's just say generate plane mesh. Thinking for a bit here. Let's get rid of this. We'll keep this drawing around. This is a 4x4. Let's add some comments. Make sure we have at least 2 vertices in each axis. Otherwise it makes no sense. to make a plane. We need the recast create triangles with one vertex in an axis. On an axis. Cool. So here we allocate vertices. Actually, I don't think we need to zero this. Let's just set the tangent to 0, which we're not using yet. I'll just put it to do here. Quickly tangents. We're not doing tangents yet. We're not going to go on that tangent, eh? The tangents, you need tangents and bitangents for normal mapping. Cool. So let's output this data. No? There we go. Let's see this. Alright, this needs to be pointer to pointer. So output these. Awesome. Now let's just do the simplest thing possible and just have one plane. So we'll create a vertex buffer and index buffer for it. Say plane vertex buffer, plane index buffer. And we want a plane index count. I'll also just store the vertex count just in case. Might as well. We don't really need the vertex count. What we can also do is, what I just thought of is test model index count, since we're hard coding that. Going off on a little sidetrack right now, but I actually think is pretty important to do. Since we're passing the index count, we need to store this. And in our test render function, instead of having this hard-coded value, we can just say test model index count. That's our plane. Right, need to write the output variables. Oh. What do I call it? Yeah, vertex count. Index count. So output variables here. Got to stay hydrated. Let's see. Right. We'll just build it in our general initialization functions, which is really big. But that's fine. It doesn't really matter. It's all prototyping code anyway. Upload, generate, upload, test plane. So let's test our function. Generate plane mesh. Let's do 512 vertices by 512. Cool. Out vertices. Vertex plane vertices. Right. We're just doing this in local variables. So that's all the output variables. Now we need to create some buffers. Vertex buffer. Descriptions. Empty. Desk.byte width is plain vertex counts. Well, I'm really starting to get tired. I can barely type. Type the vertex. I don't need some presets. Usage, default usage. Default. Bind as vertex buffer. CPU access flag 0. We're not going to access it from the CPU. Yeah. Once a buddy at university who was really confused because his rendering system was really, really slow. And he couldn't figure out why. It turned out that he was looking at the documentation for like the buffers. That's the wrong page. For like the buffers and textures, and he found these CPU access flags. I just looked at them and like, oh, there's read and write. Well, I'm going to be writing to them, so he did write because he wanted to upload this data. But writing actually means once you have created it and then want to write to it. And this actually places the texture into a place of memory that is mapped to the CPU RAM. That is really slow to access during rendering. So that's why we pass a 0. It actually says it right here. 0 if no CPU access is necessary. But they don't add that to the flags, which is a bit confusing. So this is just like one of those things you just have to know. Let's see, search a byte stride. We've done this before. It's a vertex, size of the vertex. They want the sub-resource data. Data.thesis mem. Vertices. And then we have this pitch, which I doubt really does anything in our case, since it's a one-dimensional thing. But we'll set it anyway. Span pitch slice or slice pitch? I forgot. Slice pitch, whatever. Cool, let's actually create a thing. Don't I just have the device pointer? I do not. Or do I? Ah, Telsense was just hanging. Create buffer, description, data. Let's see. Plain VB. There we go. Oh man, I'm tired. Like I've been working all day doing programming, uh, and then I get home, and what do? I turn on the stream to do some more programming. Can't get enough of programming. Okay. So let's see if we don't make too many copy paste mistakes. It's going to be an index buffer. The rest is all the same. Data is going to be different. It's going to be plain indices. That's going to be index counts. Plain IV index buffer. And then what we can do now is, since after this we basically have uploaded our data, like we really haven't. Once you get into like the more lower levels APIs like DirectX 12 and Vulkan, you'll know there's like an upload buffer in between them. But when using DirectX 11, as far as we know, the data has been uploaded, we can get rid of the buffer. So we can get rid of our plain vertices and get rid of our plain indices. We don't need this data anymore, so we can free this. So we'll get rid of it. That's everything created. Let's add it to our test render function. So I think we should reorder our function a bit based on when we change state. So last time what we did is we took this let's see if I can find the picture again. Graphics pipeline. Yeah, this picture, awesome. No, I wanted the picture, I didn't want. Can I just stick this in paint? Paint up nice. Let's see, can I zoom in? That's really small. Perhaps if I visit the page I can get a better one. Byline. Yeah, there's a bigger one right here. Let's zoom out a bit. Right, this picture. This is a really cool website, by the way. Let me plug this website. This is 3D game engine programming, 3dgap.com. This is by Jeremiah van Oosten. He's actually a teacher at the university I used to go to, the Breda University of Applied Sciences. He has some really cool stuff on here. If you want to like learn more about graphics programming, definitely check this out. Let's get back to our picture. So the GPU basically goes through this whole pipeline of different stages that it executes. First, it's the input assembly, where it basically reads data from our vertex buffers and index buffers. Then it goes through the vertex shader. Then it does, it can do a bunch of things that we skip. It puts the data into the rasterizer. Data from the rasterizer goes into our pixel shader, and the data goes into the output merger, and the output merger puts it on screen, basically. Now, changing these states can cause the GPU to sometimes have to wait for something to finish and then start a new thing. Like if you change the render target, it has to wait for all the drawing to be done before it can do drawing on the new render target. So you want to change the state as little as often. And you actually want to sort of figure out what state changes are really expensive and which ones are really cheap, and then sort of order them by that. So we will change our render function so that we sort of start doing that. So binding our render targets, let's do that at the start. And this will also sort of get us into something called rendering using render passes. So we set the input layout. Next thing we want to set is actually our shader. We want to set the vertex shader. And then in here we want to bind the constant buffer to the vertex shader. Because this constant buffer can change for every single model. Now the rasterizer state, it's going to be the same for the whole rendering. Going to be the same the whole time. Same as the viewport. We're not going to change that. Pixel shader going to be the same. Let's actually do that when we set our vertex shader as well. So we've set all the shaders. Let's see, what else do we have? With layout, shaders, the index buffer and vertex buffer. Now setting primitive topology is actually pretty cheap, but we're not changing it, so let's just put that at the start. The blend state is not going to change, the depth stencil state is not going to change. Let's move that up here. So we're sort of reordering based on when we need to set things. Now the sampler is never going to change. The shader resource might for different bottles. Let's actually add this to where we set the shader. Cool. So basically, here we have the section where we calculate the constant buffer data. We upload the constant buffer data, bind the constant buffer. We actually only have to bind it once. I just noticed. Because we just changed the data in the constant buffer, we don't have a different constant buffer. So this is all the code for drawing our what's its face, our rabbit. Let's actually add a new section here. And what we really want to do is just change what's in the constant buffer first. So we want to give this its own matrices. So we need to change the volt matrix and the WVP matrix. So let's make this an identity matrix, and let's just recalculate the volt view projection matrix. We can actually keep the view projection matrix, which is this part. We don't have to do that again. We can just do this. We have to recalculate it here because we updated the volt matrix. And then also we have to do this. And then we upload it again. So let's make this a bit more consistent. So let's just say we declare this here. And right here we'll just say world matrix is this thing, and here we also have our WP matrix, which we'll declare first and then use. Oh, double semicolon. Why are you giving an error here? Oh, I added an L here. Yeah, let's actually move this up since we set it once, but we could be setting this like more often. Cool. Now we draw the rabbit here, and then we actually change the vertex and index buffers. Change the vertex and buffer, to the plain vertex buffer and the plain index buffer. And then here we can say draw again, but with our plain index count. So to sort of recap, is we first clear our buffers, then we set a bunch of general state that's going to stay the same. That's actually this part, set some general state. Then we bind the buffers for our rabbit model. Then we calculate a bunch of matrices. Like these matrices will stay the same, but here we calculate the actual specific data for that model, and that we'll call draw. Then bind the buffers for that other model, calculate its specific constant buffer data, and then call draw again. And it's going to be draw plain. Let's see if all of that works. And it might be that our plane is inside the rabbits. I'm not seeing it. Let's make the plane really big so we can see it. So for a world matrix, we'll just do scale f4x4. And it's nice that we did the inverse transpose matrix thing, because they're already scaling non-uniformly. And it might also be that the binding order is inversed. Ah, there we go. See, the binding order is flipped. So I messed it up. So instead of doing this, we do 2, 1, and we need to do 3, 1. There we go, we have a big plane now. Now we made the plane between 0 and 1. Should we keep it at 0 to 1, or should we make it -1 to 1? Or -1/2 to 1/2? Because it's really nice if the center of the plane is in the center. Like the 0 point's in the center instead of in this corner. Let's make it, let's make it -1 to 1. So we can simply do that by multiplying by 2. Oh, and then subtracting 1. But this also moved it along the y-axis, so this needs to be, let's do this. So we force those to a -1 to 1 value. There we go. So now for a big old plane, let's make it a bit smaller. Let's make it like 20 meters by 20 meters. Oh, that's 200 meters. That's really large. Let's go for that. Let's retry. Let's take a look. All right. Big plane. Awesome, and we generated this ourselves in code. And as you can see with this point filtering, it's not doing any blending. You can really see it if we get up close. It's just plotting the pixels as they are on the texture. Our camera is broken. Let's actually... We've done the flat plane. Let's add another thing we'll do. Fix the damn camera. This is really annoying me. And it's basically going wrong right here. I think I just need to flip these. Yeah, now it's actually working. Awesome. We got our rabbit that's just floating slightly above our plane and rotating. Cool. Now I'm thinking for a bit. So if we actually take a close look at our texture, you'll see that it's inversed, which is confusing me. It's flipped, you see? Now I'm wondering if it's just flipped along the y-axis or also flipped along the z, like flipped vertically or also flipped horizontally. So, let's flip the UVs right here over plane. Yeah, now it says hello. That's better. Our camera is actually really slow. Let me add some buttons for changing the speed. So let's just say if includes left control, yeah, whatever. Let's make control make it go slow, and let's make shift make it go fast. That's not working. Oh, that might actually be broken. Let's see if I actually ever use this. I know Windows is like really weird with its it's actually GUI stuff. It's really weird with its keys. Let's debug that as well. Debugging as we're going along. So we have this event handler. Key down. Convert key. If it's shift, then we'll make it left shift, right shift. What if these are flipped? What if left and right are flipped? No. Shift and control aren't doing anything. Oh, I see something that's up. These don't have brakes. So that's definitely broken. It's always funny, like the weird bugs that you find. And like you think you've made it so that it's all bug free and cool, and then like you've tested it and then you find out it actually doesn't work at all. What also is really bothering me is that I can't see the white space. View white space. Ah, that's better. Now I can see where all these random spaces are. Let's see if this hits. Yeah, it does hit. L parameters some value. Let's look at the hexadecimal version. So if this is not set, it should be left shift. So there'll be a param will be L shift, which is A0. Then we break. Then we look that up in the conversion table, which is it's not showing up. Yeah, so position 0A or A0 left shift. 32. That matches with that. Keys down. This is doing GUI stuff. Wait, where do we... Huh? Oh, I'm looking at the wrong wind proc. Right, I want this one. Yeah, so let's restart. And shift. Convert key. We get 32, which is right. That's not key invalid. That's also not escape. So you write the key state to 1. So at 32 it's 1. But then here it's not hitting. What? Let's actually do that. Let's press shift. So we set the state. Right, and then it goes into some random thing. Now the annoying thing is that we'll also get an event for key up. Whenever we do this, let's make it run again. Ooh. Exit process, dead. Failed to create. One or more arguments invalid. The width, oh. Aha. So that's another edge case we'll have to figure out at some point. We can't minimize the window because that will just crash. We'll figure that out later on. Let's focus on what we're trying to fix. Why our shift key isn't hitting. Just... So the other keys work. Like, let's test A as well. So shift does the key down thing. Doesn't trigger that. A, it does the key down thing, and then this gets triggered. Oh, because this is now right, but with left it also wasn't working. Let's see. 32. Oh, it actually hits now. Speed is 10. So then, what was the bug? Then this should just work, right? Oh, now it's working. What did I change? Huh? It might just be this. Right, and then I had to set to right shift. So it was always sending it to the menu key. That was the bug. Well, that's now fixed. So we can use shift. Cool, so we can fly around. We can take a look at our beautiful, beautiful plane, which is lit straight from above. No, not lit straight from above, actually from an angle coming from sort of that direction. We don't have a sky map, so skybox, so it's all in darkness. Let's think of some more things that I want to do. So we fixed the camera. I also want to figure out do sRGB on my textures actually at some points. And then I also really would like to do a water effect. And I already have like a plan in my head for this. And I want to use ray tracing because ray tracing is the big thing right now, even though well, ray tracing has been around for like forever. But you got this really cool new RTX hardware by NVIDIA to speed up ray tracing. Even though I don't have one of those, I just want to figure out how like can we do some real-time ray tracing effects in our game on like a mid-range graphics card without all the cool ray tracing stuff. Just do it manually, like write it ourselves. Do that. Let's talk about that for a bit. For that, we need do ray triangle intersection. We'll need Fresnel to blend reflection and refraction. We need to calculate reflection vector, calculate refraction vector. We're going to need a spatial database or just a well, just say a bounding volume hierarchy, which will be there to accelerate the ray tracing. Yeah, that's the word I'm looking for, acceleration structure. And I want to try and make these with excellent binding objects instead of excellent binding boxes. Because I read a cool article about those. Yeah, so that's going to be like lots of cool stuff. And for the refraction and reflection, we can like ray trace specific models. For refraction, yeah, we can just like if we were to build a game where the player is not allowed to go into the water, we can sort of figure out what models are in the water, and we only have to ray trace those, so we can really limit that. And for reflection, we can do screen space reflections. And we can do skybox reflections. And then maybe so other models to ray trace. Yeah, for the refraction, well, I call them vectors, they're really rays. Ray, and then we do a ray trace model, specific set of models. Yeah, and also with the new cards that AMD announced, the Navi cards, I read that the way the caches are laid out and how it loads data, you can actually do custom data structures a lot better. So that will be really nice for a binding volume hierarchy in the future. Yeah, it's gonna be cool stuff. But it's actually getting really late right now. It's 11 o'clock here. So I'm going to end the stream for tonight. I hope I can stream some more in the weekend, but I'm not sure of that yet because I got some other plans as well. But yeah, we can definitely do the height map for the worlds. Do the sRGB stuff, and then also add some water effects. And I'll try to go look for some free to use skybox that we can use, so we can add a nice sky to our little rendering thing. So it was nice coding with you, and I'll see you some other day.